Hey guys, if you're watching this video, you have completed the Candium lab where we discovered half-life of radioactive candium. So that was really exciting and yummy. Now we're going to go back to our notes and make sure we have a solid definition of half-life. So make sure you have out your nuclear chemistry notes. You'll also want to make sure you're paying attention and getting everything down that you need. So the last set of notes we learned about radioisotopes, and we learned about how they're unstable and that they decay from a parent nuclide to a daughter nuclide. And now what we're learning is that the amount of time it takes for these isotopes to decay is different for every isotope because it really depends on that stability. Remember, we said that if the ratio was 1:1, then that isotope was very stable. The further away it got from that 1:1 ratio, the less stable that isotope was. So it's going to decay over time, and how much time it takes to decay is called its half-life. Specifically, half-life is the time required for half of the atoms to decay. So if you started with 100 atoms, it would be the amount of time it took for those atoms to decay down to 50 atoms. Okay? If it has a short half-life, it is less stable. So again, that ratio, if the further away it is from that 1:1 ratio, the less stable it is, it's going to decay really fast. Okay? So here's an example of a half-life chart. Okay, and so notice on your x-axis we've got billions of years. On our y-axis we've got a ratio of potassium 40 to argon. All right, and then also calcium, because potassium will decay to argon and then it actually decays to calcium after that. So if we've got a rock that we've discovered, and it kind of looks like a pizza with like pepperonis and then decaying into pepperoni and sausage. Sorry about that. So at 0 time, so 0 billions of years, okay, this is a newly formed rock. Most of that rock is made of potassium. One half-life goes by, which in this case, the half-life is 1.3 billion years. And now our rock consists of mostly potassium, about 50-50, half potassium, half argon, and half calcium, I'm sorry, and a little bit of argon is starting to show up as well. So that calcium is decaying into argon. We have another 1.3 billion years go by, so now 2 half-lives have occurred, and we're only left with a quarter of what we started with. So of our pizza, only 1/4 of our pizza is now potassium. We've got a lot of calcium, and then some of that calcium has even started to decay to argon. 3 half-lives go by, now 3.9 billion years, and if you think about it, guys, if one half-life was 1.3, you multiply that by 2, that gives you 2.6 for 2 half-lives. Multiply it by 3, that gives you 3.9 for 3 half-lives. And then at 4 half-lives, multiply by 4, you can see we've got very, very little of our potassium remaining. Mostly calcium and argon are what's left over. So this is a curve, a logarithmic curve, and I know you've probably seen these in a math class, but they are very, very applicable in our science class as well. They tell us lots of useful information for our half-life of these atoms. So here's an example problem. Fluorine-21 has a half-life of 15 seconds. If you started with 25 grams of fluorine-21, how many grams would remain after 45 seconds? One thing I want to point out, 15 seconds is a very short half-life, okay? It's going to be almost all completely gone in a minute. So here's how I would set up this problem. I would make yourself a little chart, okay? So make yourself a chart and label it starting amount, so that's your parent isotope, time in seconds, and then the amount that you have decayed, your daughter isotope. This should look very similar to the chart that you made in your lab. So if you started with 25 grams, 0 seconds have gone by, 0 grams have decayed, okay, 15 seconds has now gone by. We know that 15 seconds for half-life, it's the amount of time it takes for half of 25 to decay. So we should have 12.5 grams of our parent, 12.5 grams of our daughter. Another 15 seconds goes by, so we're up to 30 seconds total. Half of that has decayed. So I just took 12.5 divided by 2, got 5.25. And that means total over here, 17.75 grams are now our daughter. 15 more seconds goes by, so up to 45 seconds. Again, I'm dividing that by 2, so I got 2.625 grams remaining of the parent. Add that over here, and we have 22.375 grams of our daughter. So the answer, how many grams would remain after 45 seconds, would be 2.625 grams remaining. We're going to skip that one. Go on to fusion and fission reactions. So let's talk a little bit about isotopes and some of the reactions that they can undergo. So fusion reaction, this is when a nucleus will fuse together with another nucleus. This occurs in solar explosions and stars when they're close to the end of their lifespan. Fission reaction is when a nucleus will split into pieces. And some examples of that, this is occurring in nuclear weaponry, nuclear power plants as well, so to create electricity, and as well as in nuclear weapons. Here's an example, some more info on fission. So fission reaction, again, is when you split a nucleus into 2 or more smaller nuclei, so that you can kind of see on the atomic level, we're splitting this uranium into krypton and barium. This requires quite a bit of energy, and we've got some other particles released. 1 gram of uranium-235 will actually produce the same amount of energy as 3 tons of coal. So after it happens, after this first one happens, these 2 isotopes are highly unstable. Okay, and so that's going to cause chain reactions to occur. So you can see krypton is now splitting apart again, and then you've got more and more and more and more chain reactions occurring, releasing a lot of energy there. Fusion reactions, this is when 2 nuclei are combined to form a larger mass. This requires very, very, very high temperatures, 40 million degrees Kelvin, in order to sustain this reaction. 1 gram of this fuel is about equivalent to 20 tons of coal, so lots of energy released there as well. Occurs naturally in stars. So naturally, stars are fusing these atoms together. That's how we get all of the elements that occur on Earth. So this is super important. All of the elements that you see that we use on Earth actually come from stars. It just takes a long, long time for this to happen. So a few more applications. So here's an example of a nuclear power plant. And I'm going to go through these pretty quickly because you guys are going to do a little bit of research on it. Pretty much what happens, very similar to our power plants here that we use for coal, natural gas power plants, solar power plants, biomass, very similar structure. Here is where our nuclear reactor is occurring. We've got energy that's released, and it turns a turbine. The turbine produces electricity through electromagnetic induction, and then it comes to your house through generators and transformers. So nuclear, this energy, it is occurring. It is dangerous, so that's why we don't see a ton of nuclear power plants around. Engineers are working now to get them to be a lot more safe so that we can look at nuclear energy versus our non-renewable resources like coal, oil, and natural gas. Another application is radioactive dating. So let's say we find a fossil and we want to figure out how old that fossil is, what is the fossil, what era did it come from. We can use the half-life measurements to figure out, okay, what isotopes are present in this fossil. We can use our half-life to figure out how old it is, what is the age. The decay rate indicates the amount of radioactive material, so we can look and see at what rate is this decaying, and that will tell us how old it is. For example, carbon-14, it takes up to 40,000 years for it to decay. Uranium-238, potassium-40, takes over 300,000 years to decay. So if it's got a lot of these atoms present in that rock, then we know that we can determine its age. Okay. Nuclear medicine. So is another application. So sometimes you can, if something's happening inside your body and doctors really aren't sure what, they have these, they're called radioisotope tracers. And it's a medicine or a pill that you would take, and it's radioactive. So it will light up your insides pretty much, and it will see what's going on in your digestive system, what diseases could be present, what's working, what's not working, and why. So that is really cool. Another example is radiation treatment. So this person is undergoing radiation treatment by using gamma rays from cobalt-60. Larger doses are used to kill cancer cells. So they target specific organs in the body. There is now some new internal radiation sources. This would be in the form of medicine that you could take. Finally, nuclear weaponry. This is huge in our history. If you remember about Hiroshima and the atomic bomb, a chemical explosion is used to form a critical mass of uranium. Fission develops into an uncontrolled chain reaction. So that chain reaction, one of them starts, and then it just goes into all those other chain reactions like I showed you in the previous slides. The hydrogen bomb, this was a chemical explosion of fission and fusion. The fusion actually increases our fission rate, so these are kind of like working together. It's more powerful than our atomic bomb, so a lot more going on there. Here's an example, okay, so, and this is very, very small, okay, so you can see if this is blown up a little bit. So this is showing you Hiroshima, which was the atomic bomb, its scale, its magnitude, versus some of these other hydrogen bombs, so a lot greater magnitude of energy and explosions. This one is really cool. So I'm sure you guys have heard of the different outbreaks of E. coli that have been present lately at different stores. So I remember hearing like, there's another E. coli outbreak in lettuce. You know, you cannot buy the lettuce at Kroger, especially the bagged lettuce, the bagged salads, because there was a bacterial outbreak. I also remember hearing about some other outbreaks like hepatitis. And one thing that we can use radiation for, especially for packaged food, is to kill off that bacteria. So I thought that was kind of cool. Consumer products, so ionizing smoke detectors. This ammonium-241, it will recognize smoke, and then a chemical reaction occurs for the smoke detector to go off, and it's a nuclear reaction. One other application I thought about just now, you want to write this in your notes, even though it's not on the PowerPoint. Here locally in Carrollton, we actually have, at our Carrollton Utilities plant, where they clean our drinking water and clean our wastewater. They do that by using UV radiation. So UV light, they shine that radiation on the water, it kills any bacteria, and then they can put that clean water back into the Kentucky and Ohio River. So anyways, that is the end of our notes. I hope you enjoyed it, and make sure you have everything down.